So this video is going to introduce our key capital budgeting tool, net present value. This is going to be a dollar-denominated measure of the amount of value creation associated with engaging in a project. So three key questions that capital budgeting tools are going to seek to answer. The first, how much value does a project create, or how much money? And the key tool we're going to use for doing that is the estimation of net present value, and that's going to require us to know what the free cash flows are associated with a project. Internal rate of return is going to tell us what the rate of return on a project's initial investment is, and payback period is going to describe for us how long it takes for the project's initial investment to be recouped by investors. So, free cash flow, a simple introduction. Suppose that a simple project has only two cash flows associated with it. The first is an initial outlay, a cash flow associated with time zero. Think about putting the money in to research and development to develop a new project or to market a new product. Think about the price required to buy a piece of capital equipment or build a new plant or engage in an acquisition. Suppose that happens now, which we're going to call time zero, and suppose that initial outlay is $100 million. So obeying the cash flow sign convention, that investment is going to require a negative $100 million cash flow made today or at time zero. Suppose further that this project has one beneficial cash flow, and that beneficial cash flow is going to be $120 million, and that $120 million cash flow is going to arrive 2 years in the future. So the investors put in, or the firm puts in, $100 million of cash today and receives a benefit of $120 million in the future. So one question is, did the project generate $20 million of profit? Did the project generate $20 million of value for its investors? And the answer is no, it did not generate $20 million of value, even if it generated $20 million of profit. And the reason for that is the time value of money and the risk associated with investment in the project. The $100 million was invested up front. The $120 million of benefits don't come until 2 years later. Now, of course, we can ask what rate of return got generated by this project, and we could do that using a tool like Rate in Excel, since this is a simple two cash flow project. And so we could calculate the rate of return using either the rate function or the IRR function. We could also do it using some simple algebra. But intuitively, the question that NPV is going to try to help us understand is whether the $20 million difference between the $100 million investment and the $120 million reaped 2 years later is enough to compensate investors for having to wait and having to take on risk. And if it's enough to compensate investors, we would say the project is value creating, and that should show up as NPV positivity. So NPV is going to give us a measure of how much more the project is worth to investors than the $100 million they had to put in initially. So what is that number? Well, it's going to require discounting the future cash flows. And the discount rate that we're going to use is going to be a function of both what investors who give capital to the firm require and what corporations or firms pay in order to get that capital. Those are not two different things. So those are the same thing. The rate of return that investors earn is earned by the firm paying out dividends or coupons or other forms of cash to the investors that are greater than the amount of money they put in. So whatever that number is, we're going to call it R, and it's going to serve as a hurdle rate for decision making. When we put that into DCF, we're going to call that the discount rate. So let's go back to our simple example. Suppose that a $100 million investment initially turns into a $120 million benefit 2 years later. And suppose further that the discount rate is 10%. So think about the idea that investors require 10% return per year to compensate them both for not liking to wait to get their money back and for the risk that they're taking on. So one question that we might ask is, how much would the firm's investors have been able to earn if they had, instead of putting their $100 million into the project, they had instead put it into something else that could earn that 10% discount rate? And if you engage in a little bit of multiplication, or you could move over to Excel in order to do that calculation there, you could see that in Excel, the investors after 2 years should have some future value at a 10% rate of return after 2 years associated with an initial investment of $100, they're going to have $121 million. So investors who put their money outside of the firm into another investment that returns their 10% discount rate could generate $121 million benefit, whereas if they put their money in this project, they instead are only going to realize $120 million in future benefit. That tells us that the project is not value creating for investors and tells us, in fact, that we should estimate a negative NPV. Now, the question that NPV is going to ask us is similar to the calculation that we just did. So comparing the future value of the 100 of 121 to the $120 million benefit that actually gets realized. But instead of doing that in future value terms, we're going to do it in present value terms. So we're going to ask a slightly flipped question, which is, assuming that investors can earn that 10% discount rate, assuming that that's their opportunity cost, the rate of return that they require on their investment, how much would they need to put in to an alternative investment that earns that 10% rate of return in order to have $120 million 2 years from now? And that's precisely what a present value is. So if the future value of 100 invested is that 121, we can instead ask, what's the present value of $120 million received 2 years from now? And that number is going to be the PV at a 10% discount rate 2 periods from now of receiving a benefit of $120 million. And we learn that investors would have to invest only $99.17 million in an alternative investment in order to have a benefit of 120 in the future. So why should they put their money in this project, this firm's project, where they have to invest 100 to get that benefit, if they could instead invest 99.17 in something else and receive the same benefit? So more generally, we can add up the present values of all of the future cash flows associated with the project, add that to the cash flow associated with the initial outlay, being very careful to obey the cash flow sign convention, such that assuming there's an initial outlay, that's going to be a negative free cash flow initially. Adding all of those things together, we get the net present value. And as we've noted several times before, if we do this, as we often will, using Excel's NPV or net present value tool, we have to be very careful that unfortunately Excel's net present value tool is only going to include the cash flows associated with future free cash flows, and it's going to exclude the free cash flow at time 0. So we have to make very sure that we add that cash flow in separately, which we will. So let's move to a very slightly more complicated example. So this is a project which is going to involve 4 annual cash flows. These cash flows are going to involve investments in year 0, which we'll call today, and also an investment, so a negative cash flow 1 year from now. Imagine that it takes time to build, or that there's multiple periods worth of research and development or other forms of investment before the project is actually generating positive cash flows. So the cash flows associated with this project are negative $100 million in the first year, negative $70 million 1 year from now. So sorry, negative 100 in year 0, negative 70 1 year from now. And then we're going to have 2 years of positive cash flows, $150 million in year 2 and $100 million in year 3. And then we're done. Then the project is over. It doesn't generate any further cash flows, positive or negative. And further, assume that the discount rate associated with the project, so investors' hurdle rate, the rate of return that they could earn on outside investments with the same risk, assume that discount rate was 9%. So if we move over to Excel, where we've already got those 4 cash flows laid out in standard accounting notation, so negative 100, negative 70, 150, 100, we can calculate the NPV of the project just by discounting those 4 cash flows and adding them together. Obviously, we know several different ways of doing that. One is that we could use the PV function in Excel. And so we could calculate a PV associated with a rate of 9%, which will make sure we lock in so that we can copy this formula over to subsequent cells. This first cash flow note comes 0 periods from now. Now, it turns out that Excel's present value function doesn't mind you giving it 0 periods, in which case it just doesn't do anything. It's going to give us back exactly the number that we plugged into it, but that's going to be convenient for consistency of the formula across the row. I'm going to put in no intermediate payments because we're just going to discount a future cash flow of, in this case, $100 million received when? Well, paid when? Paid now. And indeed, since we're looking at 0 periods of discounting, that $100 million negative cash flow is going to be associated with a positive $100 million PV. Now, we do have to be a little bit careful here about signs. So first, let me just show you the cell references. I'm referencing the number of periods from row 1. I'm referencing the free cash flow in dollars from row 2 and the discount rate fully locked in cell B7. So the thing that I do have to be extra cautious of here is that when I use that PV function, Excel has flipped the sign of my cash flow. And that's on the assumption that I would have to pay $100 million. I would have to receive $100 million today to justify paying $100 million today. So since what I'm interested in calculating is actually the present values, I am going to have to be really careful here. And if I use the PV function to do this, which is not the only way to do it, but if I want to use the PV function to do this, I'm always going to have to check and make sure that I got my signs right. And since the PV function flips them, I'm going to flip that manually by introducing a negative sign at the beginning of the formula. So if I copy that formula across and then check that my references have worked, and indeed they have, you'll see that I have negative cash flows associated with negative PVs associated with the negative cash flows in year 0 and 1, positive PVs associated with the positive cash flows in year 2 and year 3, and whereas the magnitude or size of the year 0 cash flow is the same in cash flow terms and present value terms, as I move out into year 1, 2, and 3, the magnitude shrinks. And that's just that discounting the fact that money received in the future is worth less, both because of delay and risk, than money received today. Note, that same decreasing magnitude over time is also true for the cost that gets paid in year 1. So I would rather pay $1 later than pay $1 today, just as I would rather receive $1 today than receive $1 later. And so the negative cash flow in year 1 of $70 million paid shows up still as a negative present value, but it's going to be a smaller negative present value because I don't mind as much paying that $70 million if I don't have to pay it until next year. Indeed, it only hurts me or costs me as much as it would for me to pay $64 million now. So having calculated the PVs of all 4 cash flows, we can calculate the NPV of the project, and I'm going to do that here in cell B11 just by adding up those 4. And if I do that, we get that the NPV of the project is $39,250,000 approximately. So is this a good project to invest in? Well, it turns out yes. Because the present value of all the benefits added up is greater than the present value of all the costs added up, we're going to say that this is a project worth doing because it passes our key NPV decision rule, which is do the project if NPV is greater than 0. So let me just quickly show you 2 other ways that we might have calculated NPV. One more, which is kind of manual, and then the way that I would recommend you actually do this, which is to do it all in one step using the NPV function. Although, again, we have to be very careful that Excel's NPV function expects us to start by giving it cash flows in period 1, not in period 0. So one thing that we could do is instead of using the PV function to calculate the present value of each individual cash flow, if you wanted, you could go back and look at what the algebra is for discounting a single cash flow, and you would note that the algebra for discounting a single cash flow involves taking that future cash flow and dividing it by 1 plus the discount rate raised to an exponent equal to the number of years that you have to wait before you pay or receive that cash flow. And here we don't have to do a sign flip, so always worth checking. When we take the present value of a negative cash flow, we want to get the negative cash flow before we net them out. And that'll work for years 2 and 3. And it actually turns out that that formula will also work for year 0 because when we divide by 1 plus the discount rate raised to the 0th power, raising anything to the 0th power means you just get back 1 and we don't do anything. So we get the same number, $39.25 million for the NPV, and that would be an alternative way to do this calculation. The downside is you have to use a little algebra instead of the built-in PV function. The upside is that you don't have to worry so much about the cash flow sign convention. Third way of doing this and calculating the NPV would be to not calculate the PVs of the individual cash flows at all, but instead to use Excel's NPV function, which requires us to put in the rate first and then all of the future cash flows. But if I did what I just selected, I'm going to get a problem, the wrong answer, because NPV expects us to start with the cash flows in period 1. And now, having added together the present values of all of the future cash flows, I'm still going to need to add in the present value of the cash flow at time 0, which doesn't require any discounting because it happens today. So I'm going to add that in. You could do that before or after the NPV with the plus, but you do need to add in that cash flow. And note, what I'm doing is adding a negative number. So if I were to run the formula without it, what I'm getting is that the present value of all of the future cash flows, the cash flows in year 1, 2, and 3, are $139.25 million. And then since I want to subtract off the $100 million investment required in year 1, I want to subtract the 100. I do that by adding the negative 100. So the general rule as we add these things up is you always want to be adding up the cash flows, and you want to let the cash flow sign convention do its own work. So they're going to wind up being subtracted if they're negative. They're going to wind up getting added if they're positive. So 3 different ways there of calculating the NPV, all giving us, of course, the same answer of $39.25 million. So the slides lay out ways to do this, either manually using this division algebraically, or using the NPV formula, and I just showed you a third way to do that. So our rule says, when should you do the project? You should do the project if NPV is greater than 0. We're going to go ahead and call it a value creating endeavor. Why? Well, because if the NPV is greater than 0 and the NPV is associated with the sum of the present values of the initial investment and the present values of all the future cash flows, where the initial investment is negative and the present values of all the future cash flows is typically positive, a positive NPV is going to mean that those positive benefits are bigger than those negative costs. One additional thing that I would just note, a project which is NPV positive and therefore should be undertaken according to the NPV rule. A project which is NPV negative and therefore should be rejected according to the NPV rule. NPV is telling us something about the amount of value that the project has created or destroyed, and therefore whether it is a good idea or not. NPV does not tell us how much profit or even how much cash the project has generated over time. And so, for example, if we go back to the Excel and we note that we've calculated a 39.25% rate of return, 39.25% positive NPV, if we were to just add up all 4 of these cash flows, 2 negative and 2 positive, whoops. Sorry for the typo. If we were to just add up all 4 of these, you'll see that in dollar terms, the project has created $80 million worth of positive cash flow. However, it's only created $39.25 million worth of NPV. And so a project typically will create more dollars of cash flow than it does dollars of NPV. And that's because this NPV calculation is, in a sense, penalizing the benefits for arriving far off in the future. So what would happen if instead we had a project which was exactly NPV negative? And we could get there just by tweaking any of these 4 numbers. We could do this in Excel using a tool like GoalSeek. But suppose instead I just kind of play with it a little bit and I add in a number like $49.90 in year 4. So I'm just in year 3. So I'm just lowering that number a little bit to see what it takes before I get the project down to just about 0 NPV. And it turns out if instead of that final cash flow being a big $100 million, it was only $49.15, we would instead have had a project which was at almost exactly NPV 0. Now, that does not mean that the project did not generate any return for its investors. Indeed, we can see by looking back at that sum cell that this project has generated $29 million in positive cash for investors over the 3 years that it operated. But its NPV is negative. That's so weird. How could it be that a project could generate positive cash for investors while still generating an NPV of 0? Well, it turns out if we were to calculate the rate of return on this investment, and we'll do that in a minute, that would be called its internal rate of return. This project's IRR, or internal rate of return, is not 0. It has generated a return. We can see that from the positive sum of the cash flows here in cell G2. Well, what rate of return has the project generated? At an NPV of 0, the project has generated a rate of return of exactly 9%. So there is a positive return on this project. It's just that that positive rate of 9% is exactly enough to compensate investors for the delay and the risk that they're taking on by not putting their money in something else instead. So the project has generated positive cash, in this case $29 million, or $29.16 million. It's generated a 9% IRR, or internal rate of return, to be described soon. But that has resulted in a 0% or a $0 NPV, because a 9% rate of return, or making investors wait 3 years to get back $29.16 million on this investment, is not creating value. It's just barely compensating them for delay and risk taking.